All right, good morning, everyone. Let's, I guess everyone's slowly come to the aula, so let's get the show on the road. It's my pleasure to welcome everyone to this, at least for me personally, highly anticipated session, and to introduce Manuel, who will be leading it. Yeah, I'm glad we worked out the times. I hope it works for everyone. So maybe a quick word about Manuel. He has a rich history in type-driven development and reactive programming and software verification and Bayesian reasoning, and even did a stint teaching at University Bamberg, as I remember. He's also a friend of mine, so I'm particularly happy to welcome him to Ost and to this event. So without further ado, giving up for Manuel.
Thanks a lot, Alex. Yeah, I'm going to talk about a library called Rhine, or a set of libraries, you could call it a framework, that does functional reactive programming with type-level clocks. You'll hopefully find out what that means. First, I want to tell a little anecdote. That was maybe 2014 or 15. I was in the maths department, and there were not enough people who knew category theory. And so I went to the computer science department in Nottingham, and lots of people know about category theory. Great. I was happy. And then we went all to the pub on Friday, and then yeah, you go to the pub, that's what you do on a Friday afternoon. And then there was this guy came to me and said, oh, I write games in Haskell. And I was like, no. Nobody writes games in Haskell. It's impossible. It was Ivan Perez, and I got into a big FRP deep dive then, and we started toying around with Dunai, a bit with Yampa, and with Rhine, and then yeah, that sort of spun off from that. Just stopped working. No? Maybe because I need to change the focus. How about this? Okay, I'm Manuel. Yeah, now it works. What we'll do is we'll clone this repository here. We've prepared some material for you where you can work through it and program some of it yourself. The plan for the session is, okay, I'll talk about FRP, Functional Reactive Programming, and the Rhine library a bit. I hope to keep it under 15 minutes. I might take longer, depending, we'll see. Then when that's done, you should clone that repository, have it on your computer, install Haskell if you haven't done that yet. Or if you don't want to code yourself, find a friendly person here who has that and code together with that person. You can pair program. Then I'll show you how this works in principle, how you go through these problems, how you learn this. It's in some format that I've called Cohen. I found out that actually nobody knows this term. I thought it was common, but it seems I'm mistaken. That's sort of small self-contained problems that you can work through in your own pace. And there's several tracks. There's a basic track where you learn some basics, and you can work through those. And I'll come around and answer questions. I'm also going to say some things publicly if I notice that everybody gets stuck on the same thing. And after some time, we'll collect the questions, the hardest problems, look at those together, see what we can learn. And then there's an advanced track, or actually a UI track where you can do something with Gloss. And who has ever worked with the library Gloss before? So a few people. It's a minority, though. You can do vector graphics, 2D vector graphics, in a very simple and declarative way of that. And then we can try and write a little snake clone. Okay, so I'm going to tell you a lot of stuff, but you don't need to memorize everything exactly, because actually the learning materials are self-contained. So just relax, don't take notes frantically. Just let it sink in. What is functional reactive programming? So I've heard Ivan say a lot, that FRP is about time. Now, I've asked him today, he said it's actually Colonel Elliot who said that, which makes a lot of sense because Colonel Elliot is sort of one of the founding fathers of FRP, you could say. So FRP is whenever it becomes important to use awareness of time in your program, when you don't just operate on a bunch of data or have a bunch of side effects, but it's important when those happen and how much time passes between steps. So we want to somehow think about when computations and effects happen while we program. Okay, that's sort of a big hand-wavy idea where we're going to. Is this what I'm going to tell you here today, functional programming? I'd say yes. Actually, in 2019, Colonel Elliot came around and he said, I don't know whether you know me, or I said, of course I know who you are. I told him a bit about Rhine, and he said, oh no, that's wrong. That's not FRP. It's something different. Who knows? I would say it's one specific opinionated framework on how you can do things, but it's different than the original FRP ideas, but it still borrows ideas. So there are lots of different frameworks, different libraries. Some of them are very similar, like Rhine is very similar to Dunai, it's very similar to Yampa. It's completely different to Reflex, to Reactive Banana. Well, not completely, but it's quite different. So it's a big landscape. And we're on one specific point today, so I'm not going to talk about everything. There is much more, so go out, discover that yourself. Okay, first, one quick word about monadic effectful streaming, or I would call it like that. So very often you have programs that are centered around a main loop that consumes data, produces data, and performs side effects. There's lots of libraries that do that. I'll put them in two categories. One are synchronous ones, where you have one output per input. Like the typical thing you find there is something called a monadic stream function that is implemented, for example, in a library called Dunai, or also in some parts in the machines library and other libraries like Automaton that I published recently. There's also older libraries that use this paradigm. And the essential idea here is that you have a monadic stream function that is parameterized by three types. You have a monad that does the effects. It could be I/O, then this thing can do I/O all the time. It could be identity, then this doesn't have any effects at all, and then it just computes. This is the input, this is the output. So it's really a function. It's not just like a signal or an event or something. It's something that consumes events, signals, something like this, and produces other ones. And it is implemented something like, well, you take an input, you perform an effect, you get an output, and you have a new state. So you have state encapsulation. And that's maybe one of the most important bits about how you often implement an FRP system. You have local encapsulated states. And those are the building blocks of your whole program at the end. And so half of FRP is based on variations on this theme. That's why I'm talking about this, although there is nothing about time here yet. Okay, so this is synchronous monadic streaming or synchronous effectful streaming. Then there's also asynchronous, where you have many outputs per many inputs. So you might know Pipes library or something like this, or Conduit, also Streamly streaming, also some parts of machines again. There you have, for example, in a pipe, the pipe says, well, now I want some output. Now I want some input. You'll never know exactly which one it will be. It could be any. So that's why you have many-to-many relations in outputs and inputs. Okay, let's talk about FRP now. So the old thing is what we would call classic FRP now is developed by Conal Elliott and Paul Hudak back in the 90s, and that says we want to model a functional reactive program with two basic concepts that are usually called behaviors and events. There are different words for that. I think in reflexive behavior is dynamic, and so you might encounter them under different names, but the two ideas here are that behaviors are time-varying values. So you can think of it, but really only think of it, not implement it, as a function from time to your value. So whenever you have the position of some object in a physical simulation that moves around, where it is, it will depend on time. And so potentially computations can happen all the time. It could, at any time, you could call this function at any time if you want to think about it as a function. And the other big thing is events. When you have something like user input, you have a mouse clicks somewhere. At one specific instant of time, you have this click, or you have a key down, or some an HTTP request comes in your web server, something like this. And you want to think about that like a list, or actually a stream of tuples of time and values. And at that particular time, we received this particular event value. So then computation happens every time an event comes in. Okay, riddle solved. When do computations and stuff happen? Many FRP frameworks follow this idea. So the original one was functional reactive animations. That was later, that had performance problems. Then there was FRP now and reactive banana that solved those. There's Reflex, which is a big FRP system aimed at front-end development. There's many more. The other idea in the functional reactive programming world is arrowized FRP frameworks. And there the central thing is a signal function. So this here, the behavior and an event, they are both values. But we're doing functional programming. So how do you make a value from another one with a signal function? So the idea, the very hand-wavy idea how you should think about it is an SF and a signal function from A to B is something that takes a behavior and makes another one from it. But with the important condition that you can never look into the future. When you have a behavior in B and you want to know what does the B do at a particular time, this can only depend on what the behavior A does on times at that point or before that time. And that is like a reasonable invariant or a reasonable condition you want to ensure, but it's hard to implement. That's also why signal functions are not implemented like this, but they are implemented usually as something like monadic stream functions we had before. And some frameworks that work like that are, for example, Yampa is a very old FRP framework. But that didn't have side effects. Yampa is a completely pure framework. So then we started to look into Dunai to take the monadic stream function approach to add effects to arrowized FRP. And then from that, we spun off Bearriver and Rhine. And that's sort of the second iteration on arrowized FRP is if you have something like a monadic signal function, and here you can, that's what I just said, you can think of a signal function with input and output, something like a monadic stream function, the thing with the internal state, but it has an extra effect. It has a reader T time effect, which means at every step of your computation is allowed to know what time it is now. And with that really very simple effect, you can do a lot. Because you know what time it is, you can also save in the state what time it was last time. You can know what time has passed since the last step. And then you can do all of the typical signal processing things like numeric integration, numeric differentiation, all sorts of signal filters, all that kind of thing you can certainly do. It's a very powerful, very simple idea. And Bearriver and Rhine are sort of the two libraries that do FRP like that. Okay, and what is this Rhine thing now? The idea how we came to that is we ended up writing FRP applications always as big monoliths somehow. And so it was really hard to pull things apart, and especially if you have several components that run at different times, or at different clock rates, I should actually say, it's really hard to organize that well. So a typical example would be you have a game, and then you have a video at 30 frames per second, 60 frames per second. You have audio much faster, or depending on how you produce audio, maybe also much slower because you just play sound files or something like that. You might also have a physical simulation that might be very fast because you're doing some real time, or you have a very slow physical simulation that because you have a round-based game. And you have all these different rates. And some computations are on one rate, and some are on other rates. And to organize this, we have type-level clocks in Rhine. So basically, on the type level, you have one extra thing. Because we had effect input-output, now we have effect clock input-output. And we know from this clock type when we expect this component to be activated. And because it's on the type level, we actually have the type checker check that this is correct. So you can compose like synchronous components that do one input, one output each step, and also asynchronous ones, like maybe the connection between your physical model to the rendering engine that takes, maybe a physical model has 100 steps per second and your video has 60 frames per second, and you want to transport the data from one to the other, so you have what I would call here an asynchronous component that has to match these different rates. You can compose those safely. Actually, one time I was giving a talk on a different framework on essence of life coding, and while I was giving that talk, I was plugging two different things together, a web server and something else, and I did a horrible bug, and I didn't realize what the bug was. It was exactly a bug like that. You had two things at different rates, and if you don't know what the rates are and have nothing to differentiate those rates, you run into all sorts of nasty bugs. And those are caught here by the type checker. They become type error. So basically, this framework is here to answer that questions: when do the computations happen? You look at the clock and the type level. That's when it will happen. How does this look like in code? Let's look at it roughly. We have a type class called clock. And this basically says, here, this type here, this is a clock type, and it runs in a particular monad M. And it can produce timestamps. Might be UTC time, or might be double or something, or might be integer even, depending on your domain. And maybe there's some additional information about why the clock ticked. And you can have many different kinds of clocks. For example, you might have a clock that has really on the type level now here, millisecond 10, which says this clock is supposed to tick every 10 milliseconds. It says that on a type level, like this 10 is a type level number. And that only works in I/O because you need to look at the time, look at the system time. You need to do a thread delay and all. and these kind of things. So that's why the monad here is I/O. A completely different clock is it's just a singleton, is a standard in clock. This clock ticks every time a user enters a line on the console, on the standard input. So it might never tick if there is no input. It might tick very often if you pipe a file into your program. But every time one line arrives, this clock will tick once, and you're allowed one step of computation with this. So that's also in I/O here, of course, because you need to interact with the handle. But there's all other clocks that don't have an I/O monad, have other monads, or are polymorphic maybe because they're pure. And in this case, for the standard in clock, this tag type here is text. So every line is one text. And you can use that in your computation if it's on the standard in clock. You get this line and you can work with it and can do something with it. So that's how you can very quickly write an interactive console application, for example. Okay. Let's look at some example code. I'm just going to highlight a little bit what kind of things you're going to expect. Not going to explain it into detail. You can work on that in a second and think things will become much more clearer even when you work on it yourself. So I've just taken this from one example. There's a folder, Rhine examples, in the repository where you can look into examples how you would write a typical program. We're simulating a ball that you can throw and will jump and do a parabola and then fall on the ground again. Physical simulation. And we want to kick off the ball by pressing enter. So it has to be on the standard in clock. This here, so you recognize SF, that's signal function, and CL means clocked. So it's a clocked signal function. It's like a signal function, but you have here monad, clock, input, output. So every time we enter something, we enter a line on the standard input, we launch these, we launch a ball, and by that we mean we produce a random velocity, so I just take some random values from I/O, and we have this constructor here, or this function that takes a monadic action, so something in I/O, and makes a clock signal function from it. So some other concepts we have. Very often you have things that are not dependent on a particular clock. They're just a general concept, like the physical model of how things are going to move in the field of gravity. That shouldn't depend on how you clock it. Well, it might depend a little bit for like a numeric precision or something like that, but in principle, denotationally, it should not depend on it. And those are called behaviors. So behaviors are clocked signal functions that are polymorphic in the clock that don't depend on the clock. They just depend on the time domain, like the type of time stamps. And that's how it modeled free fall here. So basically free fall with a starting velocity of v0 means you take the acceleration of the Earth as a vector, you do the integral over that, so integral over time, starting at that start velocity, and then you have the velocity of the ball. If you take the integral over velocity, you have the position of the ball starting at the origin at 0, 0, 0. So you see this integral here, that's what I said before. Because we have access to the current time, we can write stuff like integrals, numeric integration, as signal functions. And who of you likes arrow syntax? I was afraid it was not gonna. Okay, so people are undecided. Who hates arrow syntax? Okay. fight. No. Okay, around the same. Sorry, I didn't raise my hand when I said I like it. Well, okay, talk to me about arrow syntax later. For now, I'm going to say arrow syntax has one very narrow field where it applies well, and that is streaming and signal processing. I think for very different applications, it's weird, but if you care about that, then give arrows a chance. Basically, what you can do here, you can write something like a lambda combined with the do notation. So you have something, you can write behaviors and clock signal functions with arrow notation. By that you have a new binder. It says, here is my input, and I'm going to pipe some input through another signal function, like the one from before that we defined here. I'm going to get some output, and I can use this output again. I have let expressions. Can use this output and use it as an input in other signal functions again. Or in this case, in a return A is an arrow built in. Yeah.
Maybe explain why it's an underscore after block.
Yeah, here, yeah, okay. So this is maybe not the best example for arrow syntax because I'm not using the input. In principle, like a lambda, when you have backslash underscore arrow something, then it means you discard the input. The same happens here. So it's a bit of a lame example because we're not really using this input. But if this was any interesting type, if this was something interesting, then we could write a variable name here, and that would be bound to the input of your signal function. And then you can use that in the computations. For bigger signal functions, it's a really good way to organize them. Okay, and there's one more concept that I want to briefly talk about. So when you have this ball, you throw a ball, it flies, and it lands. Once it lands, its behavior is completely different. It's just on the floor. It doesn't do anything. It's constantly at the same position. So the behavior changes, and I really mean it in both senses, also in the sense of behavior and the sense of FRP. You have to switch to a different behavior, and you have this switching is done in monadic FRP, and in effectful FRP is done with exceptions. And by exceptions, I don't mean I/O arrows, not those nasty things. Well, not nasty, but with algebraic exceptions in the except team monad, which is basically just either under the hood. So you can raise exceptions by just adding except t to the monad. So here I'm saying, well, when the ball is falling, it might hit the ground, which is the case when the height is below 0. In this case, we throw an exception. Right? So we look at the freely falling ball, and when it hits the ground, we throw an exception. And we have another stage that is another clock signal function, this waiting function. It basically waits on the user input. So the ball is on the ground, it waits to be kicked off again. We said before it's going to be kicked off again when you hit the console. And it waits for that exception to arrive on the input, and you can throw that exception and then launch a new ball. And you can combine these different modes in a monad that is CLSF except. That has one more type signature, that's from one more type variable. So you have a clock, again, you have input, you have output, you have the monad, where the rest of your effects happen, and the exception that can be thrown. And that forms a monad, so you can say, well, first I'm going to go into the waiting stage, then I'm going to wait until the ball is kicked off. Then I'm going into falling with a starting velocity, which was thrown as an exception before. And then I'm going to wait again until the falling behavior has hit the ground, that throws another exception. When that is thrown, we'll just start again, and we go like that forever. That's how you can specify different behaviors and switch between them. Okay, one final thing to wrap it all up. At the end, you combine all these data flow components with their respective clocks. So this start velocity, where we said whenever we hit a line on the standard in, we get a velocity, that is on the standard in clock. So this is just a singleton, so there's a single value here. Let me quickly jump ahead. The ball is, we will simulate it every 10 milliseconds. So we have to give an implementation how we achieve these 10 milliseconds, and there's one particular one in the library. And then we have to talk about how we let those two components that are on different clocks communicate. And this is done with resampling buffers. That's the concept. That's the asynchronous concept in FRP. An asynchronous component that can take in data at a different rate than it outputs the data. And you can see all of the different rates in the type signature. The resampling buffer has the monad, effects, input clock, so input arrives at every hit of the console. Output goes away every 10 milliseconds. Input type is the ball velocity, and then output is maybe ball velocity. And in that case, we're using a first in, first out buffer, so we just buffer all the velocities that come in and serve the last one whenever there's one there. Okay, and then you stick all of these together with those nice little combinators, so it's pretty clear the data flow goes in that direction. And here is where the type checker will complain if you try to stick together things with two different clocks. So this is where it will catch your bugs. And then when you have a Rhine with no input and no output, or trivial input, trivial output, you can run this with a function called flow. Okay, that's a very fast race through the library. I've taken a bit longer, so we're a little bit behind, but not too much. Sorry, this time here is not correct, of course. We'll go until at 1 hour 30. Yeah. So I'll go. Let's say 15. At 15:30, we'll maybe make a short break, and we'll collect and ask around how you're doing. So the plan is now clone this repository here. You can also, if you search for it on the internet, you'll quickly find this. Clone it locally. Install Haskell if you haven't done that. Hope you've done that. Run Cabal update, because I've just recently add a few fixes to Rhine. And then you start with this command here. So there are many little executables, and they're all organized like this. This is the name of the track, like the basic track. We'll learn some basic things, how clocks work, how signal functions work, and so on. And it has 3 chapters, and each chapter has 3 to 10 problems in it. And when you run that, it will fail at the beginning, because it's your job to fix it. There's a little problem left for you in there. It's maybe missing something, there's a little typed hole or something, or maybe there's a type error, or something is wrong, and you need to fix it. And you can fix it by having a look at the test. You can run a test here as well that will basically take your executable from there and integration test it, and when the test runs through, then you've probably fixed it. And for the first cone, I'll just show you how how that's supposed to work. It's a bit small, right? How do I, yeah. Like this? Larger? No, does something different. I think this. Is this good enough to read for you? Okay. So the first problem looks like this. So you have some documentation there where it says what you're supposed to do. So basically, it says you're supposed to output the message "Hello Rhine" somewhere. Go below. So here's an import. Rhine has like a prelude. So if you import frp.rhine, then it imports most of the things that you will use. Here's the clock that we are using. You can read everything about what a clock value is, clock type, a type level number. And here's the component that is incomplete that you're supposed to complete. So it's a clock signal function here that has effects in I/O because it can print stuff. And this is the clock it is running on, so it runs every second. And it doesn't produce or consume data because all we're doing here is a side effect. And then you can see here, there's an issue. There's a hole. And so we can put something there. We can put something like this. Okay. Does it do anything interesting now? Okay, so we can go and do a cabal run basic, because they're all numbered. You know what number you're on. Now we can run this program that we've just completed. So we'll compile it. We'll output something every second. Okay, nice, it does something now. But is it correct? So we can test it. There's a test that has the same name, but just test dependent at the end. You can run that. And that will basically run your program in a test embedding and then say, oh, okay, so it did something, but not the line, "Hello Rhine." Maybe you have a typo. Oh, indeed I do. How could I mistype this? I should have written this here. All right, so you can run it again, have a look. What does it do now? Oh yeah, this looks better. Run the test. Okay, test has passed. Awesome, so this works now. I can go to the next thing. I've done basic 1.1 now, I can do basic 1.2. I'll try to run it. And it says something, oh, there's a type error here. Nasty, so what do? I open this. And now I can look around here, maybe can read some information here about this as a bug. Can think about what this bug is. All right, and so like this you go on. The first chapter of the first track is supposed to be simpler, so I hope you're not having problems with that. If you do, that's completely okay, so always feel free to ask me any question you might have. Also, if it's Cabal does something weird or anything, come to me or just raise your hand. I'll walk around, help you. Yeah. And okay.
I can bring a microphone.
Yeah.
Can I take a question now?
Yeah. But let me just finish by saying that this one is so the first track starts simple, and then it gets progressively more involved, and the UI track is even a bit like a bit bigger problems, more problems in one file, more complicated problems. So yeah, as you progress, the difficulty rises. Yeah. Happy to hear the question.
Hi. So a behavior is a continuous value over time. Is that correct?
Sorry again?
A behavior is a continuous value over time.
Yes.
Am I right in thinking that it's useful only when it's sampled? So this is a pull-based system.
Yeah. I was confused the terminology of pull-based and push-based. I would say it's actually push-based because the clocks are the drivers behind the system. So whenever there is a tick of the clock, the system will be stepped, or that component of the system will be stepped.
Okay, and are behaviors functors?
Behaviors are
they functors?
Functors, they're even pro-functors.
Okay, so...
They're even applicatives.
Okay, so before when you were lifting pure functions to create a signal function, you could have used fmap for some of those, is that about right?
So again, you could?
Before when you were using ARR to lift pure functions into signal functions.
Yeah.
Some of those could have been fmaps instead, is that right?
Oh, sorry, I've went past that already. Like this here, for example. Like I have here free fall, and I get a position which has three components, and then I take the third. Like this together with that is just fmap.
Maybe take the bottom line here.
Yeah, that's fmap. That's true. Okay. I could have done like angle bracket and.
Sure. Okay, thanks.
Yeah.
Yeah, if there are any other theory questions, so to say, feel free to raise your hand.
Yeah, there.
What was continuous? So was it that a behavior is a continuous value over time, or
yeah?
What was it? So
you
what
should
does it
think
mean,
about it like that.
With respect to which topology, which notion of continuity we're talking about?
That's a good research question, which we never completed. So that's also the problem that Colonel Elliott has with this. Because at the end, your behavior is going to be sampled at some particular clock. Like it forces you, the framework forces you at some point to choose a clock. So you have to sample it at some point. But the behavior is polymorphic in the clock, and by that, so you can write behaviors that are not that should not be behaviors in the sense that they depend. For example, something that just counts the samples. That is, in a sense, a behavior that breaks a law that we haven't formalized anywhere. But what you're aiming at, I think, is you should think about having clocks and finer clocks, that a clock is finer than another clock if it ticks at the same times and potentially at further ones. And like that, they form, in a sense, I think it is a lattice. And that gives you a notion of convergence. And basically, if your behavior is independent of that, like if you can go on finer and finer clocks and your behavior converges under that is what really behavior should be. And something like numeric integration or just counting the time or a constant function is of that kind. But it's true that the framework allows you actually to write a few things like counting the number of steps, which are not of that kind and which sort of break that illusion. Does that make sense?
Thank you. Thank you.
Okay.
Yeah, I was a bit confused about the resampling because
Right.
you said that everything has to have one, yeah, so the resample function has millisecond 10 as part of it. So I would imagine that resampling took things that were 2 different clock rates and sort of did an impedance mismatch. So somewhere I'd see maybe a millisecond 1 and a millisecond 10, and it would adapt between them.
Yeah.
But here I only see millisecond 10, so.
Yeah, oh, yeah, the other thing is the standard in clock. That's the other clock rate. But that is an, how do you say, an unpredictable clock rate. What's the right word?
I see.
A non-deterministic clock rate. So this is a special case where you have input arriving at a rate that you can't control and output having to go in a particular rate. That's also why the output is a maybe, because your buffer might run empty and then you can't output anything. But there's other examples for buffers. There's also what you mentioned, like there's, for example, when you use pure clocks that don't have effects. That also works. I haven't talked about that at all. And there you can actually take these numbers on the type levels and really say, okay, I put in a vector of length n, and I get out a vector of length times that clock rate, or times that interval size larger. Like I have a millisecond 1 clock, a millisecond 10 clock, and I can ensure I put in 3 samples, get out 30 samples on the type level.
Okay, thank you.
All right, I guess if there are no questions right now, I'll mute myself for a moment and I'll just come around and let me know how it's going for you. Just one thing, because a few people asked, what is this resampling thing? I've really skimmed over this, so there's no surprise. It's hard to follow. So in Rhine, there are 2 kinds of components. One are synchronous in the sense that they have one output per input, and the other ones are resampling buffers, which can have many outputs to many inputs, and how many those are depends on the clocks. So let's first look at one step. Actually, well, yeah, that'll be good enough. Just this here, clock signal function has 1 clock. This is this here. This says that input here is going to come at this rate. That output here is also coming at this rate. So we put 1 maybe ball velocity in there, we get 1 ball position out. A resampling buffer means it has 2 different rates. You can think of a resampling buffer as something like with a little internal state. You don't see the state directly, it's encapsulated in this buffer. But you can access it by giving it input, and you can get information from it by demanding output from it. But you don't do that directly, but the framework does that for you. So in that sense, resampling buffer is a push-pull component. I think somebody asked us something about push and pull before, because you have 2 clocks here. This is the input clock that pushes data into it. I hope I'm using those terms correctly. I always confuse those. Yeah, okay. And the other one, yeah, all right. So it pushes data in that, potentially updating the state. In that case, because it's a buffer, it just puts 1 value on the buffer. And the other one pulls a value from it, so it demands a value from it. And then from its internal state, it can compute an output value and potentially also mutate that state in that case when taking 1 value from that stack and returning it if the stack is empty. And so, is that coming closer? So when you want to compose those, like here, you have these funny combinators here. This one here says, but basically, you should think about it like this. This is a big arrow that can convert between different clocks. That there are different clocks present, you can read off from this type signature. This type signature here tells you there are two clocks in this whole program. One is the standard in clock, and the other one is millisecond 10. And they're composed with this construction here, which is a sequential clock, which basically says they both run at the same time, they run concurrently. But that is on the left side of this arrow, and this one is on the right side of this arrow. So this basically says this data arrives here at standard in clock until here, goes into this buffer. This is where the clocks change. So this half here is activated at a different clock than this bit. So at the end, when you build your Rhine program, you have a big signal graph where you have lots of different components, and they're not activated all at the same time. All of them are activated at different times depending on which clock they are on. Makes more sense? Yeah.
What does this program exactly do? Is it like every time you hit the standard in, like you hit the button, the simulation starts again?
Repeat the question.
Yeah. The question is, what does this main program do? Does it just does it repeat the simulation of the ball every time you have input there? Let's see whether we can answer that question by looking at the code a little bit. So let's go backwards. So we have this start val Rhine. Yeah, that is basically just start val at a particular clock value. So we've said, okay, this is the complete component on this clock here. We've collected all of the parts of this component together. The same for ball Rhine. It says, okay, this is the whole component that I want to run on the millisecond 10 clock here. What do the two components do? So let's go a bit back and look at start val. So start val is activated whenever there is a line on the standard input. We output a random velocity. And ball is the combination of a few different things. This is the more complicated bit. That says, well, we go through these different ball modes here. We switch between the waiting and the falling mode. And when do we? So when do we switch between these modes? So this mode here, waiting mode. When does it end? For this, we need to have a look. What are the exceptions that are thrown in this? So let's look here. And the exception is thrown whenever there is an input. Whenever this input here is just a velocity, we'll throw an exception. The other mode, this one here, falling mode, discards the input. So that doesn't throw an exception on input. It throws an exception when the height of the simulated ball, so we let the ball fall, and we throw it and let it fall, and whenever the height is below 0 when it hits the ground, then it throws an exception. So whether it will react on this input here depends on which mode we're in. Okay, so because we switch between these modes all the time, sometimes we're in the waiting mode, then it will react on input, and when we're in the falling mode, it will not react on that. Okay, so if we plug all of that together, we can hit the keyboard, we can hit the return key, and we'll get events on this clock. I'll deliberately said events because it's not a behavior, it's really only when we press the return key will we have a value there. So that's why this clock is really an event clock. That fills up that buffer, And it will be consumed very quickly, every 10 milliseconds. Values from that buffer will be consumed. So at the next step of the physical simulation, we'll have a value available already. So if we pressed the standard in clock recently, we'll get an event, we'll get a new velocity, and use that. Then this here is just velocity, and then it will enter this function here. Maybe I can try and can just run that example if you want to see it. Just need to recompile it. Does it make more sense, or is it still, yeah?
So is it the case that I can hit the return key a lot of times, and every time it will generate a new random velocity? But the simulation runs at least 10 milliseconds before switching to the next velocity.
Yeah. So if the ball flies all the time and you hit it all the time, the buffer might be empty before it hits the ground again, and then it doesn't start anew. But you can change that behavior by using a different resampling buffer. There's different ways you could do this in principle. So this outputs the position all the time. I hit enter, and then throws the ball, catches it again. Do that again. When I throw it, I can press it many times. You see, okay, the buffer was so full that it did one more throw, but not. Yeah, that's what would happen. All right. Another question?
So we are talking about clocks and time. So is this notion of time? It's real time.
Yeah. So it's actually parametric in the notion of time. You can use UTC time. I think I have an example. Yeah, I haven't talked about this in detail, but in the clock type, you can also specify what the type of timestamps is. So you can use UTC time. I mean, most of the time you'd use that. But you might also want something like a simulated time of some kind, and you can use any floating point number or another real number. You could also use something round-based, then it's an integer, but yeah, most of the time you'll think of it as some kind of real time, yeah.
Okay, so it's possible to also use some more like abstract logical time that doesn't have to correspond to any wall clock time.
Yeah.
Okay, thank
absolutely, you. Yeah. Yeah, so there's big section that I didn't really talk about where you have pure clocks, where you basically specify how they tick on the type level, and you can schedule them, and they will schedule in a deterministic way. So the framework is general enough that you have both those paradigms at hand. You can schedule them in I/O, and then they're not deterministic, but you can do a lot of real life stuff with it, or you can do it in a pure monad and have deterministic scheduling. Okay, maybe let's pause at this point, and can I just get a quick show of hands? Like, how many of you have been able to run this at least, install it and run? That's awesome. Yay. Very good. Well done. Who has managed to complete like the first 3 or 4 problems? Still very many. Awesome. Okay. So who has managed to complete the first chapter? Okay, and the second chapter, like basic 2. Okay, so we're like sort of towards the end of the first chapter. Is there already something like typical problems that you came around? Does somebody want to shout a specific number that maybe you could solve or couldn't solve, but that was hard, or was something that was hard to get? Somebody want to shout a number? Or a word, like title? Can you raise your hand if you say, I just want to hack on more? And then okay, there's also quite a few people. Sir?
It's not on Google.
Why would it not be in Google?
Is it in stackage?
Oh, fuck, yeah. Right, if you do set stackage. Yeah, you're right. Well, I'm confused. Wasn't there a time where just everything from Hackage was on Google? Is that not the case anymore?
Was it long ago?
Okay. I'm old, it seems. Yeah, okay, that is a problem. I can see that. Okay, I don't have a good solution for this not being on Google. So the best thing I think you can do is just go on Hackage for the documentation. If you mean to find a particular function or something like this. Yeah, so I've tried to complete, like, to insert links to the pages where you might find something. Yeah, but you probably need to just go through the Hackage. The Hackage page and look at this. Yeah, okay. I didn't check that. Yeah, okay. Okay, let's go on like this. Let's give this some more 5, 6, 7 minutes until 3:45. And have a look around whether there is anything particularly any problem you'd like to see explained in detail, or we can look at it in more detail. Just some quick notes on if you want to do the UI track, where you can write a snake clone, you have to install some kind of OpenGL. And there's different ways how you can do this. If you use an NixOS or something with Nix, you can use a Nix expression like this and save this as shell.nix, thanks to Endgame. It's on the Discord channel in the FRP, so on Discord in the FRP channel, so that should work. But what you can also do, I didn't write that on the README, but if you use any Debian-based system, look at the .github/workflows/CI/YAML, and you will find a command that looks like this, that will install all the dependencies you need for a Debian-based system like Ubuntu or Debian. Yeah, so choose either of these methods. If you have on Mac, it works, but I don't remember how you install it. I'm sorry, I didn't look that up. I sort of added the UI track a bit on short notice, so I forgot to look into that. And on Windows, I have no idea. I don't know if anyone has ever run Rhine on Windows. Tell me if you do. Okay, so how are we doing? How many of you have completed the first track? Oh. Can you raise your hand if there was anything that was like outstandingly hard or something where you thought, well, there's something missing in the explanation. I don't get why it works like this. Yeah? Let me know. Sorry again, what is? The difference between clock signal. Oh yeah, excellent question, excellent question. So, clocks are both types and values. You have a type for a clock, and that is used like a type level tag to distinguish which components or which parts are on that clock. And then at some point you want to run this thing. And to run the clock, you have a specific value. So I didn't write it down here, but here's something that tells you, given a value of that type of the clock, how do you run it? It's a bit like, I don't know whether you've ever used servant. It's like when you have an API and you have that as a type, and then you have the handler that actually goes through that API and routes this thing, and that is a bit like the value for the clock in a sense. So you have these two concepts for clocks. Okay, now we have, does it not work? We have CLSFs, clocked signal functions. So at first, these are really just signal functions, hence they have input and output, and they have this type level tag here. What this gives you as an extra effect is that this here is able to access the time of that particular clock. It means it has access to this timestamp here and to this tag. So you can use that in the definition of a CLSF. Okay, so CLSFs compose like this here. You can, well, okay, that's a bad example. So like here, you have here you have 3 different CLSFs. You can combine them with this operator. Tons of other operators where you can use them to combine them. You can compose them using arrow syntax or whatnot. You can build up bigger CLSFs from that. Okay, fast forward to Rhines. Here, you say, okay, I have now combined all of the CLSFs I want in that particular component. I'm going to bundle it up with a clock value of the right type. That is now a standalone thing that can run on its own. Like a CLSF can't run on its own because it has no clock, it has nothing that drives it. It just says, how would it behave given some timestamps? And a Rhine is a complete thing that produces its own timestamps and reacts to them in some way. And I didn't show you here, but you could also take, for example, this here and run this separately, principle. And then you would have a monadic stream function, in fact, that produces these ball velocities at specific times. Or you could also have this here, and it compiles to monadic stream functions, or actually to automata in a sense. And if you combine several of these components together, such that there are no inputs and no outputs left, so that this doesn't need to interact for data with the rest of the world, then this is a standalone program that does everything, all the clocks, all the scheduling of the different clocks, the routing of the timestamps, and the different signal functions in there, in one thing. Make sense? Okay. Right. Okay. Let me ask again: who's in the second track, or who is in or past the second the second chapter? Who is in or past the third chapter? Oh. Has anybody started with the UI chapter so far? Well done. Yeah, okay. So so that's basic 1.3. 3.3. Oh, okay. Oh no, sorry, did I break something there? Okay, let's have a look. Okay, you mean the test is wrong, maybe? That's weird. Okay. Surprising. Let me have a look. I'm not sure. I think maybe my reference implementation is wrong, but I can't see why it should be.
Your input is 24 characters long.
But it's replicated.
You repeat it 20,000 times. So by right, the final count should be 24 times 20,000, i.e. 48,000, not 56,000.
No, there's, for the characters, you also have to count the new lines. So you have 3 more, it's like 27.
But then, oh, I see. But where are they supposed to come from when you count them? I mean, you don't get the new lines, right? When you get the... Or,
I think the standard WC counts the new lines.
no, but I mean in the...
What do you use here? Like, how do you do?
Are you supposed to add them manually?
Well, I can add them very elegantly.
I mean, sure, I mean, you do this, but... Oh, so you're supposed to do that, you mean?
Sure.
Okay, I see, okay, sorry,
Yeah.
my bad.
No, but that's sort of the trick in this problem. FRP.
Should I get an error in this this exercise number 7?
Yeah.
So when I so it's basic 1.7 compose on the same code. Oh,
Tests.
yes. Now
Okay.
Das mit den Gloss Clocks, das raff ich nicht.
Okay, vielleicht sollen wir das durchmachen am Ende.
Aber das ist wahrscheinlich noch eine Weile hin für die Arbeit, ich weiß es nicht. Ich meine, ich habe den Riss geskippt.
Ja, andererseits sind die ist die Zeit gar nicht mehr so lange hin.
I just started the gloss section and I have a question. So I saw that the very first or like the second gloss tab, like whatever these are called lesson. So we do the like inside some kind of parametric thing. We create the picture and also run the effect of painting. Right, so we have this.
Yeah.
But wouldn't it be much nicer if we had a pure network that for each time step could compute just the description of the picture, and then externally, like completely outside the network, we would have something that paints it.
Yeah, I've sort of toyed around with it. You're absolutely right. But there's some weird asymmetry in input and output because I can't find a good way how to say where that output goes. Just in the type signatures. Maybe so. One thing I thought about is you could just have a writer monad or something like this.
Right, of last picture or something. Yeah.
And then you evaluate that writer monad, and maybe this is the right thing. Maybe I should have done that. But
it's not really like okay. But with the writer, you kind of still have the same problem, right? In that it's the effect of like let's say you use the last monoid, so it would be like last tell wins, right? But then you have the same problem that you have this network, but the effect of it, which is not really in the structure of the graph, right? Because it's an effect. It's like on the side. It's not a side effect, but it's an effect of the side, and that's what drives the drawing. So it's not apparent from just the graph itself. But what you would really want is the output of the graph, like the result in the arrow
Yeah.
sense, shouldn't that be the picture? Like, shouldn't it be an arrow that goes from, I don't know, like time and user input or something to picture?
Yeah, but usually that's also what I do. I mean, let me have a look at the code, but usually I have one signal function that just computes that, and then you put it into another one.
I mean, I'm only at the second example yet of the class start. I did the first one, but you look at the second one.
Yeah. Yeah, there we're not really using. Oh, sorry, that's. Yeah, we're not using that
you would
much.
hope that translate the circle. That is your picture, and the fact that you paint it is somehow should be incidental, or not even incidental, but it's like outside, right? Because that's
Yeah, maybe do the third exercise and let me know.
Okay.
Well, let me try again. Do people want to shout in a particular problem that was weird, that was hard, or where they didn't learn how to solve it properly, that you want to have discussed? Or are you just happy hacking on?
No, I'm just having problems with this.
Oh yeah, me too. Let me know you solved all of them.
That's the third track.
Yeah, so for the UI track.
The next track is the third track.
Oh.
No, I'm not having trouble. Oh, well, I just gave up.
Is the lost clock UTC thing, is there something you added yesterday or something?
Is it? Maybe, potentially. So it's not so new it's not so old. It's in the last version, I think.
I did it not in scope, although I think I did this time. So I think here.
Welche Version?
So I think is that correct? Visualization clock classical. So I don't know why I would take it.
Vielleicht hast du. Welche Rhine-Version hast du?
Ich benutze einfach nur die Next-Gen. Es kann natürlich sein, dass die falsch ist. Das würde.
Wenn du die Shell machst und dann Cabal Build All -F Solution, sollte es durchlaufen. 1.4.1 ist eigentlich richtig. Vielleicht
ist es nur ein Haskell.
Vielleicht ist das ein Language-Problem. Ja.
I have a general question about the Rhine library.
It's a last chance for anyone to name a problem that they want to have discussed in public. Otherwise, I'll just,
Well, this isn't really a problem. I just had a question.
Yeah, a question is fine as well. Yeah.
When I was reading other materials about FRP, I forget the name of it, but it emphasized one of the important things about FRP was that when you compose two streams, there's a defined semantics for how they compose. So, for example, if you have a stream and it has an event that happens at a certain time. You have another stream that has an event that happens at the same timestamp. Then when you merge those streams, there has to be defined semantics for how those two events combine.
Yeah.
You can't just arbitrarily say, well, sometimes this event wins out of the other one, and sometimes that event wins. Okay, there has to be a rule in
Yeah.
Is that a factor in Rhine, or how?
Yeah, so that is a detail that I haven't talked about much, like how does this scheduling actually work for the different clocks? I just said, well, this depends on the monad. So there's a separate type class for that. It's called monad schedule, and there are, depending on which monad you're using here, there will be a different way to resolve that question, basically, and that also determines the order in which the different steps are going to perform. I can't really summarize it very briefly, but you have different choices. Like in I/O, for example, how it works basically is that every clock runs in a separate thread, and they communicate over the standard GHC concurrency variables. And there's an M bar somewhere, and the clock that gets the M bar first, that will tick first, and the corresponding component is going to be called first. So, for example, where this matters is here exactly in the resampling buffer. You might ask, okay, will I put a value first before I retrieve it? Because if it's always the other way around, if I always retrieve it first and then put it, it will always be stale, or it will be gone, or there will be not a value there. If you go over I/O, it will really depend on just the side effects. Yeah, I think for I/O I can't really say much more than that. But there's tons of other monads that solve this question in a different way. For example, if you don't have I/O anywhere, then you have some kind of deterministic solution to that problem, and then you will have something. Then there's a certain guaranteed order all the time, and I believe for a sequential clock, it's always the clock on the left will always go first. So in a resampling buffer, you will usually, if you have for the most deterministic scheduling monads, you will have first input and then output on the resampling buffer. But then again, there's many different choices.
Sometimes you might want a mono that says, okay, if I have two events that happen at the same time, I just use their mono identity to combine them into a single event.
Yeah, if you want to merge two things, yeah.
My screen, I guess if I have a screen, I get them online.
If some two events fire on the same moment here, they fire on the same clock, right? If there are really two different clocks, then I know, for example, in reflex that will fire in two different length frames. You can't say, oh, those two external events will never fire exactly at the same time.
No, that's okay. I only care about it if they're on the same clock.
Yeah.
So if they are already on the same clock value, then you will never actually encounter them in scheduling as such. Then you will encounter them basically before this slide here. So when you do this here, you really say, everything that is on this clock is that. So this is where you've already combined stuff in a monoid, something like this. For example, the clock signal functions are applicative, so you can combine them with applicative and then do mappend at the end, or semigroup appending. And you do that before you launch it on a particular clock. So, but your question is if they are on two different clocks that happen to tick the same time at some point. Yeah. Okay. All right. Yeah.
I think I wonder if the thing that Manuel
Yeah.
Independent of the clock frequency.
Yeah.
You should get the same result. So in other words, clock frequency shouldn't be observable.
Yeah. And in a sense, that's true. Or like philosophically, that's somehow true. But then at the end, even if you go from that pure standpoint, at some point, you will eventually sample it. Let's say you have a nice reactive animation and you've defined it completely purely without any reference to a clock. And you make a GIF of it, or a GIF, I always forget, GIF, I think. You'll choose a sample rate at that point. And the FRP framework, like the FRAN, has no way to deal with that by construction, because it can't talk about that. Rhine can talk about that. It can say, well, here you have a behavior, and now we put it on a pure so-and-so many frames per second clock and draw samples and make pictures at that particular rate.
Right, but if you do have to sample at some point, but I think resampling is what messes things up. So if you have, let's say you have classic FRP, and you just add a single clock to it with sampling. Now compare that to using Rhine, and then you start out with just a single clock at the end. But now we're going to add other clocks in between and do some resampling. That, ideally, according to Manuel and Elliott, adding those extra clocks and doing resampling shouldn't affect the result.
Yeah.
But it does.
Yeah, if you specify them, yes. Yeah, that's true. So my claim is basically that. Let me go a step back. I'm not talking even about Colonel Elliott, but talking about Yampa. Like in Yampa, you don't have effects. You have signal functions, but you don't have effects. And how you write a Yampa program that actually does something. You need to add an ugly I/O mess in front of it, and at the end of it, you have to get the input and do something with the output somewhere. And this is always a mess. There's a big monadic function, something that does your I/O at the end. It's not in the framework, like it's standard Haskell, and you have to deal with it somehow. And it has the same kind of components, or the same kind of components that you have in your signal graph. They replicate on the outside as well. Like you have 3 different kinds of events. You need to somehow cater for all of these events in your I/O thing that gives you the input. And you have no way in Yampa to talk about that. And Dunai and Bearriver was the step to basically to blur the lines between this pure signal processing graph and the ugly I/O that we would rather not like to look at, and combine it in a more general framework where you can add the effects and make both, like have both in one framework, blur the lines. And you can recover Yampa by taking Bearriver and saying I do for all M in the monad. Or put in the identity monads, same thing basically. And then you recover, semantically you recover Yampa. And the idea here in Rhine is that you have all these real world clocks basically that will eventually sample things. But you can also, since it's parametric in them, you can also have behaviors that don't have a clock, so you can run them on any clock. And the way you can specify programs in there, that is supposed to model this ideal world that Conal is talking about. And the abstraction is not 100% clean, because you can also encode a few things, as I said earlier, that are not like this, but that is the idea, that's the motivation.
So if you just run everything with the arrow syntax and if you only had one sampling step at the end, then it should work like classic FRP.
Yeah, it depends. Yeah.
You only have one clock in your whole system.
Yeah, right. Yeah, that's true. Yeah, if you have like if you give the control of the clock to something external, like you would have to do in Fran or so. Also, you'd have to say at some point, okay, I'm going to sample this at some point now. If you give that a control away to somewhere else, then yes, then that should be pretty much the same. Yeah, so I'm trying to bridge a real-world gap here somewhere that.
Just gives you more flexibility, but you can still recover the
Yes.
pure behavior.
Exactly. Yeah. All right. Okay, we're finishing. Yeah, we're coming to the end of the session. I just want to briefly show you what happened if you. If you complete the UI track, you get a little game at the end, just so that you can see how it works, that you can see that it works. So I have to rebuild it. So I have a little snake clone here where you can go around. The black thing is the snake. Can eat apples and turn around and grow. Yeah. It's not so realistic.
It's a vegan snake.
Yeah, exactly. It's a vegan snake. That's why it eats apples. Yeah, and if it crashes into the wall, then it goes game over. So that's how. Where you can go in 6 steps if you do the UI track. So I'm going to be around here all Zurihack, so if you have any more questions, feel free to come to me at any time, and I'll happily hack together with you on anything FRP related, Rhine related, also other things Haskell related, whatever you want, if your setup doesn't quite work. I completely forgot about one thing that, but I'm going to pitch it at least now, quickly. So yeah, you can reach me. Also, I'm not so much on Discord, but I'll try to have a look in the FRP channel every now and then.
You really need to have matrix.
Yeah, I don't even know what my matrix thing is. Posted in the FRP channel. Yeah, I'm on Matrix somewhere as well. I don't know where. Yeah, I'm also on Mastodon, where I post funny things about Haskell or things that I find funny. And if you want some more ideas what you could do with Rhine to play around a bit, you could write your own clock. You can take a WebSocket, connect it to something that serves WebSockets. And you can take a package like was or a WebSocket package to make a clock that ticks whenever one frame from the WebSocket arrives. You can build a simple application that can talk over WebSockets. You can also you could build a web server. By taking a simple package like Y, and that again you will have to write your own clock for that. It basically ticks whenever there is a request coming in. Something that I didn't talk about at all. One of my major motivations to do FRP is actually to do machine learning in real time. There's another package that integrates Monad Bayes in Rhine, and you can do some basic machine learning with it, particle filters and some stochastic process modeling, and you can build a physical system, simulate it, and try to estimate the state of some stochastic system. You could use that. In principle, one could use that to maybe do machine learning on a robot or something, some controlling device. There's also another Rhine package that is called Rhine Terminal that is for terminal applications when standard in clock doesn't cut it anymore. And it should be really easy. I haven't done so, but you could maybe port the snake application that you get from the third track. You could just port it to the Rhine Terminal backend, and then you have a console application where you can play Snake. That'd be pretty neat. And if you want a challenge, you might have heard of the FRP zoo, because there are so many FRP frameworks out there. It's really not hard to write an FRP framework, so that there are so many that often people don't even know which ones exist, which ones are maintained. There's a repository, the FRP zoo, that just implements the same game on the same application. It's not really a game, same application in different frameworks. And I've never come around to actually put in an entry for Rhine there. So if you want, as a challenge, you could do that. Okay, coming to the end, let me just quickly thank to a few people. Thanks to Malte for alpha testing my whole the Ryan Cohen's repository. That was very helpful. Thanks a lot, Alex, to invite me. Also, thanks to the whole team of ZuriHack, of course, but to you especially also that you've written quite a few Ryan Ryan something libraries. Put them on Hackage. Yeah, also to you, I think June is not actually here, but for contributing the Rhine Terminal application, Rhine Terminal library. And I guess Ivan is also not here because he already knows all this stuff, but I've learned a lot from him and we had a lot of fun writing all that stuff together. That's it. Thanks for coming. So.